All right, let's quickly go over the solution. Okay, so for the metal semiconductor contact, it was in reverse bias. Oh, first of all, you should notice that it's p-type because in the flat band portion, the Fermi level is closer to the valence band. So you should have recognized this p-type semiconductor material. So we're talking about majority carrier holes. So if you look at the barrier for holes to move from the semiconductor into the metal, you can see that there's a significant barrier to flow. And so this is reverse bias, okay? Because in equilibrium, when the Fermi level is flat and you draw the edge of the valence band also close to the Fermi level, you can see that the built-in potential is much smaller than what I had drawn. So anytime you increase the potential barrier for majority carriers to flow across the junction, it's reverse bias. Okay? And under equilibrium conditions, you have less voltage drop in the silicon, so the width of the depletion region is reduced. So qualitatively, you should have drawn a flat Fermi level for equilibrium and the width of the depletion region decreasing. Yes, question? That's correct. No. VA is positive for voltage applied on the metal. So whether or not it's positive or negative really has nothing to do with forward or reverse bias. Forward bias means you're making it easier for carriers to flow across the junction. Reverse bias means you're making it harder to flow across the junction. So in the marked version of the lecture notes, I've drawn this for p-type semiconductor. Right? Reverse bias is for VA positive. Forward bias is for VA negative. So it's just the opposite for contact to n-type. But I didn't ask you if VA is positive or negative. I asked if it's forward biased or reverse biased. So by definition, reverse bias means it's hard for current to flow. Forward bias means it's the direction of bias that's easy for current to flow.
So when we are using VA, we have to define that as the positive.
Okay, so VA is the voltage applied between the metal and the semiconductor for a metal semiconductor contact. And so yes, VA is positive if the voltage on the metal is higher than the voltage on the semiconductor. That's correct. But I didn't ask that. I asked if it's forward biased or reverse biased. So then you look at the potential barrier. That's right. It is. It is. It still is. Right? So here, you're absolutely right. So on this quiz question, it is positive voltage on the metal side. But I didn't ask that question. Yeah. Because more fundamentally, you should just know the reverse means like hard for current to flow, and forward is easy. Okay. Yes, question, Lewis. Narrower? Uh-huh. Oh, okay. Okay, that's fine. So qualitatively, as long as you don't show it's equal or larger, then it's fine. Yes. Yeah, so in equilibrium, yes.
So what if I did?
Oh, you moved it to left up? Yeah, that's perfectly fine. Okay. That's valid. As long as you show a constant EF across the diagram. Yes, that's fine. Still correct. Okay, the width of the depletion region really only depends. There's a formula, but this quantity in the parentheses is just the total voltage drop, or across the silicon, and that's 1.6 EV. Okay, so all I had to do was put 1.6 here, and I always try to pick numbers that easily cancel out. Okay, it's just so if you have some weird numbers, it's usually that you're probably plugging in the wrong numbers. Okay, so it works out pretty easily, and if you know the dopant concentration is 10 to the 17th, hopefully you remember from homework, roughly the depletion width is around 1/10 of a micron. Okay, so you can call it, do a sanity check. Oh, okay, so the doping concentration over here in the red on the left. So again, this was from the first homework. I mean, you had this, right? It's 0.42 EV, so that's 7 times 60 millivolts, 60 millielectron volts. And so you know that the hole doping concentration is 7 orders of magnitude larger than intrinsic. Yeah. Okay. And VBI, so hopefully from your equilibrium band diagram, you can easily see that the built-in potential is just this Schottky barrier minus this small distance between the EFS and EV. And you know what that is because you know it's 0.42 EV between EI and EF. So it's just arithmetic, so it's 0.26 EV. So as long as you show an earnest effort to do the arithmetic, I'm not going to, I mean, if you did some math calculation errors, I'm not going to take off points. Okay, as long as you show some reasonable effort to make the calculation. Okay, so under forward bias now, how does the current in the diode change as you increase the temperature? So the answer, anything, if you just mention something about, okay, first of all, the correct answer is the current increases, so you get 1 point if you say that. But then you have to provide some qualitative explanation. So just something about the number of holes with with sufficient kinetic energy to overcome the barrier, the potential barrier. As long as you say something about kinetic energy, that's fine. Okay, and number of holes with high kinetic energy increasing is fine. Okay. What did you say? Said something like energy. So what do you all think? You think that should qualify? Yeah. Okay. Fine. It'll qualify. Yeah. Josh? Mobility? Oh, okay. So did you say mobility? So current decreases? Mobility. Okay. I don't think mobility is in the. Mobility is not in the equation for the Schottky-Diode forward current. I don't think it is. It is effective mass, but which is partly related to mobility. But okay, okay. So you say mobility increases. So why does mobility increase as you increase temperature? The graph. Wait, the graph shows. Okay, so we have the typical graph from the lecture is like log of mobility versus log of temperature, and you remember it looks like this. Unless it's very heavily doped, then it might increase around 300 Kelvin. So even for 10 to the 17, around 300 Kelvin, mobility decreases as you increase temperature. So if you use mobility as the reason, mobility actually decreases with increasing temperature, so the current should decrease. So as long as you're consistent, if you said current decreases because mobility decreases with increasing temperature, then you would get full points. But if you said something that's not consistent, then maybe 1 point out of 2. Okay. Okay, this one just electrostatics. So hopefully you know that with increasing reverse bias, you have to have more potential voltage dropped in the silicon. So you need to have a wider depletion region. So that's the key thing here with the part B, with the red dashed lines. Okay. And the key thing I'm looking for is a wider depletion region, and that the slope over here stays the same because the dopant concentration is not changing with the bias. Okay. The peak electric field, so from Poisson's equation, the change in electric field over the change in distance is going to be related to the charge density. But in this case, you can just say, okay, E naught is the total change in electric field, and the depletion width is the total change in distance. So the ratio of those two should be equal to the charge density over the dielectric permittivity of the semiconductor. So it's a relatively simple arithmetic calculation, 10 to the 5th volts per centimeter. Any questions on, yes, Paroma? Oh, that's fine. Okay, yeah, you're right. It is supposed to be negative. You're right. Did I get rid of some E naught? I guess. Okay, I forgot to paste. Yes, you're right. It's negative E naught, negative 1.6 times 10 to the 5. That's correct. Okay. Well, hopefully it's obvious it's negative, so I won't be picking on the sign. Yeah, because I drew it negative. Okay, so why does the Schottky diode have small signal capacitance? So the answer is basically the amount of charge that is stored on either side of the junction changes with the applied bias, or the applied voltage. So when you change the voltage, you have to change the charge. So that small signal capacitance is defined to be the amount of change in charge required for a given change in voltage. Okay, that's just the definition of small signal capacitance. So you have to add current, you have to flow current, displacement current, to charge or discharge each side of the junction when you change the voltage. So that represents capacitance. And then in an ohmic contact, how does it flow? As long as you said tunneling, it's fine. You don't, ideally, you'd say tunneling through the Schottky barrier, but as long as you say tunneling, you'll get the full 1 point. Yes, Trent. Oh, so you just do IV characteristic?
Yeah, because I don't know, like,
Ah, okay. Oh, okay, so you didn't know I was asking about the physical mechanism. Okay. Okay. Okay, that's fine. That's acceptable then. Any other questions due to misunderstanding?
I thought you were asking like in which direction it was going, so I said.
I see. Okay, I guess all those I could justify as being correct answers. All right, that's fine. I'll be more precise in my questions in the future. Okay, so the final question, hopefully by now it's really quick for you to see that, okay, this is an N-type material, 0.3 EV is 5 times 60 millielectron volts. So the electron concentration is 5 orders of magnitude higher than Ni. So the equilibrium concentration of electrons is 10 to the 15, and for holes is 10 to the 5. Now when you shine light, this is, I guess, done in class and also as homework. So the generation rate, GL, times the lifetime, tau sub p, you just take the product. So 10 to the 20 times 10 to the minus 7 gives you 10 to the 13. So you know in steady state, after a long time, the excess carrier concentrations are just going to be equal to 10 to the 13 per centimeter cubed. 10 to 13 is negligible compared to the original, the equilibrium electron concentration. So electron concentration doesn't really change much. Therefore, the quasi-Fermi level for electrons doesn't move significantly. But for holes, you're changing the excess carrier concentration is much greater than the equilibrium concentration. So the sum is going to be significantly different than under equilibrium. So the quasi-Fermi level for holes will change position from the equilibrium position. And since it's 3 orders of magnitude higher hole concentration than intrinsic carrier concentration, it's just 3 times 60 millielectron volts separation from the intrinsic Fermi level. Okay, so hopefully you actually don't have to write all these equations out by now. You should be able to quickly. So for questions like this, it's fine if you don't show all these calculations. I'm just showing it just in case some of you haven't become familiar with this approach yet. But anyway, from now on it's fine if you just know right away, okay, that's just 5 times 60 millielectron volts, 10 to the 15, okay? All right, so in the end, what happens if the minority carrier lifetime is doubled? So it takes twice as long to recombine. So you can actually end up with twice as many excess carriers at the end, and it'll take twice as long to get up, well, roughly, twice as long to reach that final value. So just qualitatively, you show something higher and takes longer to get there, it's fine. That's all, you'll get full credit. Okay? So assuming that all of your correct answers based on your understanding are acceptable, how'd you all do? Did you do all right, or are you starting to get overwhelmed? Stupid mistakes. Okay, well, but these mistakes will, it'll be worse to make them on the final exam. So hopefully you won't make them on the final exam. Okay. All right, great. So hopefully, well, we'll report the results next time. All right, so okay, were there any questions left over from the last lecture? I know it's like getting hot in here. Okay, so one thing I forgot to mention for breakdown, junction breakdown, I always like to try to give you a physical picture of what's going on. For tunneling breakdown, physically, what's going on? So this is when both sides are heavily doped. So let's say you have an N plus side and a P plus side, or P plus side and N plus side. And so the depletion region is very narrow. It actually is easier to break that down because the breakdown voltage is small. Bless you. So physically, what do you think is actually happening? I'm just going to exaggerate here. So if you apply some reverse bias voltage and you allow the energy states in the valence band to line up with the conduction band states on the right with the states in the conduction band. First of all, this distance, this depletion width is very small, so it's less than 10 nanometers. You know, roughly, a minimum, how much voltage is being dropped across the depletion region? More than 1 volt, right? Because the band gap is like more than 1 volt. So it's more than 1 volt dropped across less than 10 nanometers. So that's more than a megavolt per centimeter. So it's a very high electric field. So what effect does an electric field have on electrons? Or it exerts force, right? Electrostatic force. So if the electric field is really large, that means you're exerting a lot of electrostatic force on the electrons that are covalently bonded. Right? So now you have, in the silicon covalently bonded electrons, high enough electric field that you can actually just rip the electrons directly out of the covalent bond. Right? So that's what's happening with what's so-called band-to-band tunneling. Right? You're tunneling from a allowed energy state in a valence band. That means it's covalently bonded electron. The electric field is so high that when you apply this reverse bias voltage, you can actually just rip an electron directly out of the covalent bond. Right? You don't need like any avalanche or absorption of light or thermal energy to allow the electron to escape. Okay, so that's the sort of physical picture of what's going on with quantum mechanical tunneling breakdown. But that only happens if the electric field is really high, and that happens when the voltage, this voltage drop, this work function difference between P plus and N plus silicon is dropped over a very short distance. Okay. All right, so today is not a very long lecture. We're just going to cover, so that was one non-ideal behavior for a p-n junction diode. So today we're going to talk about additional deviant behavior, okay, devious behavior. So basically, we touched upon it. There were some questions earlier last week. What happens at very low voltages and so on. So there's just a few things that are odd about the real measured diode current characteristics. So when I first showed the ideal diode characteristics, somebody asked, okay, why do the measured characteristics look a lot different than the ideal curve? So that's what we're covering today. We already covered this phenomenon, right? So this is reverse breakdown. That's what we covered last time. So notice on the left, I'm plotting current on a linear scale, okay, and on the right, under forward bias, because you have orders of magnitude change in current under forward bias. So I'm plotting the current on a log scale. So this is the semi-log plot. Okay, so let's focus on reverse bias current. So the current's on a linear scale. Do you remember ideally what does the current look like under reverse bias? So if we look at the ideal diode equation. Okay, I'm going to have problems again. The ideal diode equation, I is equal to I naught times e to the q VA over KT minus 1. So if you keep increasing the reverse bias, the magnitude of the reverse bias. So let's say if VA is much less than 0, what do you expect the ideal diode current to look like? It's just minus I naught, right? So we expect it to be flat, okay? In other words, constant and not really dependent on the applied bias, because this exponential term is just going to be negligible compared to minus 1, even more so as you go to more negative bias values. But in reality, the magnitude of reverse bias diode current increases slowly and before you reach breakdown. Okay, so we're going to talk about that. Under forward bias, the two things that are not ideal. Okay, so just to review this 60 millivolt per decade slope. If you take the log base 10 of the current, You can take, it's basically, okay, the log of a product is equal to the sum of their logs. So you can derive this, you can express the log of the current like this as just a constant plus QVA over KT over natural log of 10. So this term is actually, let's see, VA over KT over Q natural log of 10. Right, so this is just VA over 60 millivolts. Oh, so yeah, 60 VA over 60 millivolts. So what this means is that if VA increases, if VA changes by 60 millivolts, then this term here on the right will change by 1. So in other words, on a log scale, that means by current changes by 1 decade. Right? So that's what I mean by 60 millivolts per decade. So that's the ideal. But in reality, first of all, at low current, so at low voltage, so like maybe quarter volt forward bias and below, the slope is different. Okay, it's not 60 millivolts per decade. It's actually closer to 30 millivolts per decade. Well, something like that. And then at very high voltage levels, it's also less than, sorry, it's greater than, wait a minute, this is not right. It's, okay, this is 120 millivolts per decade. Sorry. So this is also greater than 60 millivolts per decade. In other words, you need to change the voltage more to get a certain change, like to get 1 decade change in current. Okay? So you have more than 60 millivolts per decade. So usually then in the industry, when we characterize a diode, we usually write for forward bias conditions only that, so the current is usually this -1 here is negligible for significant large positive values of VA. So I is written as approximately I naught e to the QVA over eta KT. Okay, so eta is the, what is it called? I wasn't sure if it was non-ideality factor or the ideality factor, but anyways, apparently it's called the ideality factor. And so ideally, so the closer that eta is to 1, then the more ideal your diode is. In reality, eta is very rarely equal to 1, at least across a wide range of voltages. So the closer eta is to 1 of a diode, in reality, the more ideal we say it is. Okay, so today's lecture is just these three points. What is the source of those 3 non-ideal behaviors? So let's start with, well, let's just look overall. For a couple of those behaviors, it turns out that our approximation that nothing is happening in the depletion region, that carriers are just flowing through, that's actually not a very accurate assumption. So in reality, we have either recombination or generation. Okay, so we know there's various kinds of carrier action, right? There's drift and there's diffusion, but generation and recombination can affect current as well through the carrier concentrations. Okay, so let's review. For the general case, so not only under low injection conditions, low-level injection conditions, just in general, you can write this equation for the net generation rate. So the net rate at which electron hole pairs are being generated per second. So this is equal to Ni squared minus the Pn product. Okay, so let's remember, in equilibrium, okay, if we're under equilibrium conditions, what is the value of that numerator? 0, right? Okay, so under equilibrium, there should be no net generation and no net recombination. Okay, but now if we're out of equilibrium, like in the depletion region, well, we have a depletion of carriers, right? And, okay, so in the depletion region, the Pn product, do you remember the law of the junction? What was the law of the junction? Like e to the q. So Pn equals Ni squared, but it's exponentially enhanced by the applied bias. Okay? So if we're under forward bias, then the p-n product is greater than ni squared. If we're under reverse bias, the p-n product is smaller than ni squared. Okay, so let me see if I have to write. Yeah, so let's just write this down. So there is net generation electron hole pairs ni squared is less than np. So this is under in the depletion region under reverse bias. Okay, then conversely, if, wait a minute, sorry, did I write it? I wrote that wrong. Sorry about that. This is like n, okay. N is less than ni squared, right? So if Pn is less than ni squared because of reverse bias, then you'll have net generation of electron hole pairs in the depletion region. Okay, so that means the rate of change of P and N with respect to time is positive. Now, if the rate of generation is negative, that means there's net recombination. So there's net recombination of electron hole pairs if Pn is greater than ni squared, which is the case for forward bias. See, on the next slide, all right. Well, I'll just draw it on the whiteboard. But if we look at the depletion region of a p-n junction, so this is sometimes a point of confusion. So I'm just going to draw the energy band diagram generic for a p-n junction. Okay, so let's say within the band bending region, that's the depletion region, you have generation. So an electron moves from the valence band to the conduction band. Okay, so you end up with a hole in the valence band and an electron in the conduction band. Okay, first of all, which direction is the electric field pointing? To the left. Okay, so which direction are the electrons going to go? To the right. Which direction are the holes going to go? The left, right? So you generate an electron hole pair. Okay, now where do these electrons go? They go to the right, to the n-type side. Holes go to the left, to the p-type side. So if you're looking at this p-n junction diode, basically, as I mentioned, electrons and holes flow out through the metal contacts. So majority carriers flow out through the metal contacts on either end of the diode. So you basically have, for each electron hole pair generated, you have the electron going to the right, which is negative current. So that contributes negative current at every location. Well, I mean, it generates negative current. Eventually, it flows past all of the locations to the right. For the hole, it flows past all the locations to the left. Right? So basically, it's like one charge on the net, one charge flowing through this, like one electron flowing from the left to the right. Does that make sense? Right? So the point is that an electron hole pair, when you generate it, it doesn't lead to 2 times the current. Right? One electron hole pair contributes 1 charge per unit time to the current. So that's why if you want to figure out what the current is due to net generation in the depletion region, you have to integrate the rate of generation of electron hole pair generation throughout the depletion region. So every single electron hole pair that's generated is going to contribute 1 charge worth of current to both sides of the diode. Okay, right, and you have to integrate it across the depletion region so that's from minus xp to xn, and the current is integrated across the whole volume. So that's across the cross-sectional area of the diode. Okay, so this equation up here was just, we don't have time to derive it in this class, but it's the same equation that was shown weeks ago when we were talking about, for the general case, the general equation for the generation rate. Actually, I think we gave it to you as the recombination rate. It was just flipped sign. Okay? Okay, any questions just generally about this slide? Okay, so let's talk about the two cases. First case is reverse bias. So every electron hole pair that's generated is going to give rise to electrons flowing to the right, and one electron flowing to the right, one hole flowing to the left. And so that's going to add to the negative current. Okay? Now what happens when you increase the reverse bias on a PN junction diode? What happens to the width of the depletion region? Increases, right? Because it increases with the square root of the total voltage dropped across the junction. Okay, so it turns out, okay, how did we get to this equation here? And this used to be a homework problem. I'm not going to give it to you this year, but basically if you substitute this expression for the net generation rate into this integral, and you take the assumption that N and P are much smaller than N1 and P1, because for reverse bias, you have fewer electrons and holes than under forward bias. So with that approximation, if you make these two terms negligible compared to the N1 and P1, you can get a simple expression, well, somewhat simple expression for the recombination current. But the key to note is that qualitatively it makes sense. The wider the depletion region, while you have more volume in which you're going to actually sweep an electron to the right, an electron to the hole to the left to generate current. So if you have electron hole pair generation out here, right, what happens if you have electron hole pair generation out here? This really, like, they're just going to move around there and eventually probably recombine. Right? So actually that's why we draw a Fermi level out here, because this portion, this quasi-neutral region of the PN junction, those are in thermal equilibrium. So there's not going to be any net generation or recombination. Yeah, all the time you're going to have generation, and then all the time you'll have recombination. But here, before those generated carriers have enough time to find each other and recombine, they're already swept out by the electric field. Okay? So really, only the carriers that are generated within the depletion region are going to actually contribute to additional negative current. Okay? And T naught is sort of representing some kind of an average time between generation events. Okay? So the more often you generate an electron hole pair, the higher the recombination, the generation current. So and notice it's negative. Right? Okay, so that explains qualitatively then why the current under reverse bias isn't flat. It actually increases to become more and more negative as you increase the reverse bias. Okay? Any questions on this non-ideality? No. Okay, how about forward bias? So under forward bias, according to the law of the junction, you have Pn greater than Ni squared, so you have net generation. So you have you're flooding the depletion region with exponentially more electrons and holes than or under equilibrium. So there's more and more probability that some electron and hole will recombine as they're passing each other or about to pass each other in the depletion region. Okay. So what does this? Okay, so it just turns out then that this particular recombination current has this voltage dependence. It actually, so this is where the eta is 2 comes from. Okay, so that's qualitatively, you just need to know that the voltage dependence of the recombination current is exponential, but it's QVA over 2 KT. So it's not as strong as the normal diffusion current. Okay. So qualitatively, that's all you need to know. Okay, so the question is, why, if you plot the log of the current, so okay, so this is what happens. At low voltages, well, okay, can't do that. At low voltages, this slope will be, it'll be KT over Q, 2 KT over Q. Or one, okay, the inverse slope will be 2 KT over Q. Okay, That's just, right? That's like, is it 2? Yes, okay, it's 2 kT over Q. That's right. Proportional to 2 kT over Q. Okay, so the normal diode current has a steeper dependence. Okay, I'm not drawing that perfectly accurately, but it's going to be more like proportional to. Okay, so okay, I'm actually drawing the inverse, writing the inverse slope here, right? Okay, so the inverse slope for the normal diffusion current versus this is the recombination current, the slope is steeper. Okay, so hopefully it doesn't matter like exactly where they cross over, but the fact is that because the green curve is steeper, so the diffusion current, normal diffusion current has a stronger exponential dependence on voltage. At some point, it's going to become smaller than the recombination current, right? Because the recombination current has a shallower slope. So basically at low voltages, and that typically happens around 0.2 volts for a silicon diode. So at very low voltages, you're not going, that's why the slope looks shallow. But then at higher voltages, okay, so the picture is that you always have this, you'll have this recombination occurring. That's going to increase as you increase the voltage. But eventually, the rate at which the diffusion current increases with increasing voltage overtakes that. So at some point, the current that flows in the diode under forward bias is going to be dominated by diffusion. And that's in this region. So that's why the total measured curve, let's draw black. So the total measured curve is going to look something like that. Okay, so in reality, when you measure a diode current on a log scale versus voltage, there'll always be some region close to 0 where the slope is not as steep. And that's because you have extra current that's now significant compared to the diffusion current due to recombination of carriers in the depletion region. Okay, so I think I alluded to this last time. I'll draw it here. So under forward bias, you have, again, you have majority carriers flowing into each contact under some positive bias like this. So some of those carriers will have enough. So this is to supply carriers to diffuse across the junction. Let's draw it this way. So let's draw electrons diffusing across the junction, and some end up recombining in the depletion region. So basically, the contacts, right? The metal contacts have to supply holes for diffusion into the N side, and then electrons diffusing into the P side. But they also supply carriers to recombine at the junction. So that's why this current and that extra current to supply carriers recombining can become dominant at low voltages. Okay. Right. Any questions about this cartoon? I guess, so carriers that don't have enough energy to go over the barrier, but they actually can have enough energy to recombine, to meet up and recombine in the depletion region. So the question is, practically, how can you extend this region of ideality? Okay, that's a good question. Does anybody want to offer a guess or? That's a good point. You change W. So if you make the depletion width narrow, then the chances of this happening, because it's just less distance for this to happen, that could reduce it. That's true. But then that means you have to dope the junctions heavily, and you might not always want that. Okay, so there's a key requirement for recombination to occur. So what is that? Traps, yeah. So there are these allowed energy states in the conduction band, within the band gap, right? And so that's kind of hinted at here in this equation, right? There's depending on the energy level of the traps, they can be more efficient for recombination or not. So the key is actually, if you really want to have minimal recombination occurring, you really need to make sure that there's very few crystalline defects or metallic impurities in the semiconductor at the junction. That way you can minimize the recombination and generation current. So it'd be more ideal. Yeah, so in practice, well, of course, it's not that easy to have a 100% pure semiconductor. So there always will be some impurities. So the more pure your semiconductor is, the more expensive it's going to be. So there's a trade-off like between cost and do you really need it to be, completely pure. For some applications, like if you're making a very sensitive p-n junction detector, particle detector. So sometimes people make very large p-n junctions to detect particles like high, I don't know, from the universe or something, right? I mean, very low levels. Then they go to extreme pain and cost to make the single crystalline semiconductor very, very pure, no defects, very expensive. But like in an integrated circuit, a little bit of leakage is fine, So it's all cost-driven, right? We learned from the Moore's paper. So at some point, it's going to be good enough, and you're not going to try to make it, even better. It's not going to affect let's say, the circuit performance very much. Okay. Yeah, so that's basically it. You just can. Oh, so as I mentioned before, usually when you form a p-n junction diode, in reality, you start, let's say, with, normally we start with a p-type semiconductor. Then we blast n-type dopants, like arsenic or phosphorus, into the surface. Okay, so we just blast them in here. So there might be arsenic ions implanted there. Then we have to heat it up at high temperature to heal that crystalline damage so that atoms can actually rearrange and form covalent bonds so the arsenic can sit on lattice sites to become donors. So a lot of research has gone into how to properly anneal the silicon. It turns out that if you anneal it too quickly, you actually end up with a lot of crystalline defects in that. So, the best way is to actually maybe heat it up more gradually and at moderate temperature, like only 550 degrees Celsius. But then it takes too long. So, and then the solid solubility at low temperature is not as high, so you can't get as much a high active dopant concentration. So there's a trade-off. So people have developed fancy annealing techniques to heal the crystalline damage and then to activate the dopants. So it is important for forming this, eventually forming a n plus p junction to minimize the number of crystalline defects right here, because that is what will lead to high junction, reverse bias leakage current. Yeah. Mm-hmm.
So if you
So that's a good question. You heat it up to, let's say, 1,000 degrees Celsius, and that's what's done. Actually, nowadays we just melt the surface for a brief period of time, millisecond. And if it cools fast enough, the dopants are frozen in. They don't come back out of the lattice. But you're right. So with the melting approach, if you freeze it, but then later if you anneal it at 600 degrees, some of the dopants will come out. So you have to avoid really anything above 400 degrees Celsius. Once you get really high, super high dopant concentrations activated, because you originally melted the layer. Yeah. Okay, so that's it for reverse bias and also low voltage forward bias. So the final thing is what happens at high forward bias. Okay, so one thing I didn't really quite make clear because it's kind of confusing is when you apply a bias to a p-n junction, you're lowering the potential barrier for carriers to diffuse across the junction. So you have excess minority carriers in the quasi-neutral regions. It turns out those are quasi-neutral regions. So in order for them to be quasi-neutral, you also have to have majority carriers, excess majority carriers in the quasi-neutral regions. Okay? So normally under low-level injection, the excess majority carrier concentration is very small compared to the equilibrium concentration. So we sort of ignored it. But if you lower the potential barrier to diffusion enough, you inject orders of magnitude more minority carriers to each side. The side that is more lightly doped, okay, let's see. The side that's more lightly doped is going to have a lower, so this side is more lightly doped in this particular example. So the side that's more lightly doped has a lower equilibrium majority carrier concentration, right? Okay, so that side is going to first be in danger of not being in low-level injection anymore. So as you increase the bias, okay, so remember, as this distance, which is equal to this distance, right? This represents e to the q VA over KT. So as you increase VA to be really large, so e to the q VA over KT is really large, you're going to enhance the minority carrier concentrations at the edge of the depletion region. It turns out you're also doing the exact same thing for the majority carrier concentration because in reality, delta P is equal to delta N in the quasi-neutral regions. Quasi-neutral regions. So we'll talk about this next time in the charge control model. But essentially, when you set up this exponentially decaying profile of excess minority carriers, what the metal contacts are also then have to supply majority carriers to come in to match those excess minority carrier profiles to achieve charge neutrality in the dope source strain regions. In the dope P and N regions. Okay, so whenever you change the voltage on a PN junction diode, you actually have to supply majority carriers on each side to not only change the depletion width, but also change the charge stored in the quasi-neutral region. So we'll talk about that next time. So it's just that for majority carriers, that excess charge was always negligible until now. So now if you go to very high forward biases, you'll start to affect the majority carrier concentration profile significantly. So the diffusion current of majority carriers becomes significant. Okay, so in this example, we're looking at electrons as the majority carriers on the right side. And now there's now a significant concentration gradient of the electrons on the right-hand side. So which direction will the diffusion, due to that gradient, occur? Which direction will electrons flow? Due to that concentration gradient, to the right, right? Because they go from high concentration to low concentration. So electrons, under high-level injection, there will be diffusion of the majority carriers, and that diffusion current actually counteracts the normal diode current, right? So this is negative charge moving to the right. That's negative current. So in other words, as you increase the forward bias, you're not going to be able to increase the forward bias current by the same amount anymore, because now the majority carrier diffusion becomes significant and counteracts the diffusion of minority carriers. Okay? So all you need to know is that under these conditions, the current is proportional to the e to the q VA over, it turns out to be also over 2 KT. But we're not going to derive that. All you have to know is that it just increases more slowly with increasing bias. Okay? All right, so this is, yeah. Okay, so qualitatively, does this make sense? That the diffusion, so majority carrier diffusion current becomes significant, and that reduces the diode current. Right, so normally you have log I, increasing like this. Now you're not going to, if you're at high level injection, you get less increase in current for a given increase in VA. Okay, that's all it's saying. Okay, but usually before that happens, you see practically, depending on the specific diode, you can actually see this effect. It's more likely that this effect comes into play earlier. Okay, so again, on the lower left here, we have the current on the log scale versus voltage on a linear scale. So you have normal slope here. Okay, so when I post the slides, I'll change the slope to be slope rather than inverse slope. But again, if you actually flow if you're starting to flow high level of current, right? So we're talking about, let's say, a current here. If we want to increase the applied bias, increase the current flow in the diode, if there's significant resistance, okay, so let's say, because these are doped semiconductor regions, they have some length, some cross-sectional area, some resistivity, so they have some non-zero resistance. So maybe on the order of 1 ohm. Okay, so 1 ohm, okay, so what is a typical voltage based on the homeworks? What is the typical voltage that we apply to a diode? less than 1, right? Less than 1. Okay, so how much current do you have to flow through this resistor to have a voltage that's significant compared to 1, like a tenth of a volt? 500. 100 milliamps. So, okay, so once you hit about 100 milliamps, then the voltage dropped across this, the voltage lost across these resistors is going to be significant. So then you have to take that into account, because the voltage that you apply to the diode is no longer going to be really equal to the voltage that you're applying across the junction. The voltage across the junction determines the barrier height, and that determines the current flowing. Okay, so bottom line is that, make sure I can sketch this properly. You'll have some, okay, so here, so ideally, as you increase the applied bias, you'll have the current, continue to increase exponentially. But this is if, this is the current that flows if you have this junction voltage, right? So this current here, so you know the current, the voltage actually across the junction should be like here, ideally, if you're reaching a certain level of current. Okay. But in reality, you have this additional voltage dropped across the resistors. So this here, this difference here has to be due to the difference. So, so this difference is the current times the series resistance, right? Does that make sense? So when you apply a voltage externally to the diode, some of that actually does drop across the junction, and it's that voltage that determines how much current flows. The rest is dropped across the doped source drain regions. Okay? So if you actually can plot, ideally, you know ideally what the current should look like as a function of voltage, and you can plot this difference, this delta V, okay, delta V, as a function of current, that's shown on the right. The slope will give you the series resistance. And typically it's pretty small, like let's say on the order of an ohm. So that's why you don't see it until you go to high currents. Okay, so remember last time somebody had, I think in the past, had asked, in a PN junction diode, can you ever apply a forward bias, like to flatten out the curves, or to even make the curve bend the other way? And the answer is no, because if you increase the voltage that much to make the potential barrier go down that much, the current will increase so much that you're going to see high-level injection effects, or this kind of series resistance effect. You're going to have joule heating, because you'll have power dissipation. The diode will heat up, and basically it'll melt before you can even completely eliminate that built-in potential. Okay? So high-level injection effect and series resistance practically limit the applied voltage across the junction, so you'll never get rid of the built-in potential completely with any applied external bias. Yes, question? Oh, that's interesting. So can you heat up the diode by running current through it to anneal it, to heal it? That's, yeah, what happens probably is that the dopants on each side will start to diffuse also, so you won't get a nice, perfectly abrupt junction. You might start to get like a linearly graded junction. So, yeah, because the time scale. So when we anneal it, we try to anneal it in very quick, like seconds or milliseconds. Here, if you're heating it up, the joule heating process to heat up and cool down is much slower than that. So, like things will diffuse, and you won't have precise control over the temperature profile in your diode, because you have conduction. You're not going to get uniform heating. So in a manufacturing process, we actually put it into a furnace or uniformly illuminate the wafer with light to heat it all up at once and bring it all down. And if you locally just heat it in a device, then you're not going to get nice uniform dopant activation and things like that, and recrystallization. That's a good question. Okay, I think that's it for today. If you want to take a break, there's, I think, Chinese food today for the social hour.